This is the first example problem associated with lecture 1, and I'm finding out that YouTube doesn't like long videos, but there's a bunch to say about this and I don't want to rush it, so I think I'm going to break this problem into 2 videos. And so let's get into the problem. Okay, so that's not good. So this is a problem with a RAM. So essentially what we're going to do here is take a RAM and sum up each of the values in the RAM and display that result. Okay, so this is the first problem we have where we're working with a RAM, and there's a couple things to notice about these problems. So every time we work with a RAM, there's always an issue of how to address the RAM. And so every single RAM we ever use in this class is going to use the output of a counter to address the RAM. So, so initially, we already know 2 devices that we need for this circuit, which is going to be a RAM and a counter. So if you look at this RAM here, it's a 32 by 8 RAM. 32 is the number of things or a number of chunks of data it can store. Each of those chunks of data is 8 bits long. So 32 by 8. So the important thing here is I know I need a counter on this thing. So the question is how wide of a counter, how big of a counter, how many bits on the output of the counter do I need? So these problems are pretty contrived in that sense. These RAMs always have, they always can store a binary number of things, or we'll say 2 to some integer values. So anytime I look at these problems, I look at how many things I need to store. In this case, I need to store 32 things. 32 is a well-known binary number. Not binary number, but it's a well-known 2 to a certain integral power, particularly 2 to the 5th. So 2 to the 5th is 32. That means for this problem, we need a 5-bit counter. So with a 5-bit counter, I'm going to have, let's see if I can draw on this thing here. 5-bit counter, I'm going to have 5 bits. It's going to have a range of numbers. That's going to go from all zeros to all ones, which is 0 through 31. And if you can tell, this is actually 2 to the 5th minus 1. Looks like 2 to the n minus 1. This is a real classic thing we use quite often. 2 to the n minus 1. You'll see that come up later. So anyway, that's the range of numbers we get in this thing. And notice that 5 zeros through 5 ones, that's 0 to 31. That's 32 different things. Those are going to be the 32 addresses of that RAM. And so what else is cool in this problem? Whenever you address these problems, the way I like doing these things is, I think we went over this in another slide, where I try to understand the problem. Next thing we're going to do is plop down some modules on this thing and then connect them up. So for a problem like this, I like to say these problems sort of do themselves, because, obviously I need a RAM. That's one object. Anytime I have a RAM, I need a counter to address it. There's another object, and I'm going to keep reading this thing. And what is it going to say here? Continuous display the sum. It's going to sum up all the values in this thing. So in particular, I need some type of adder, in particular a ripple carry adder, since that's the only one I know. And additionally, I need to set that up as an accumulator. Hopefully you worked with an accumulator in your other class. It's just a special configuration of essentially ripple carry adder, which is a combinatorial circuit, and a register. So something like a problem like this, where you could see something like a continuously displays something blah blah blah, that pretty much means that value is in a register, and I'm continuously displaying it by not changing that value, and I don't change that value by not loading a new value into the register. So problem like this, in general speaking, I am going to start the counter at 0 and step through all, it's a 5-bit counter. I'm going to step through 0, 0, 0, 0, 0 through 1, 1, 1, 1, 1, which is 0 through 31. It's going to step through all those values, and every single step along the way, I am going to add the value in that RAM to my accumulator. So anytime I have an accumulator, I'm going to accumulate values. The very first thing I want to do in a problem like this is to clear that accumulator. I want to get that accumulator started at 0. So it works out very nicely with registers such that I can clear the register. So that starts the register at 0. So that register I'm talking about is actually the register in the accumulator, the register that is associated with the ripple carry adder. So what else do I need in this thing? Well, I think that's about it. The only thing I'm missing here is these problems are classic problems that I need to essentially control with a state machine. So these problems all have state machines, and now the state machine in this problem is essentially going to be reading the status of the circuit and sending out control signals to control the circuit. And actually looking at this problem, I actually noticed I forgot something on this thing. Essentially, I need some way to start this sequence off, and essentially usually I will say like a go signal. So that's a go or a start or something like that. I usually say go because it's only 2 letters. So essentially what the circuit is doing is waiting for that go signal. When it gets that go signal, it does what it's supposed to, which is sum up all the values, and then it stops and it waits for another go signal. And so essentially the thing I'm going to do on this thing is wait for that go signal, and when I get that go signal, I am going to clear that counter, the counter that's addressing the RAM, and then I'm also going to clear that accumulator. So those are 2 control signals right there, and I'm thinking that's all I can think of as kind of a prelude to this problem. I'm kind of bummed that I forgot to put the go signal in here, but oh well, I'll catch that in the next one. Okay, so that is the build up to this problem. I didn't really draw much onto it. I'm actually going to save this as a video and then start the problem again, and actually, we already have a head start on this. It'll be less explanation and more so just plop the needed stuff down. So in the end, I'm going to need a circuit here. The circuit's going to include a state machine. Because I have a state machine in the circuit, I'm going to need to include a state diagram in the circuit as well. And that's all I have for this problem. Signing off.